All right, hey guys. So I'm going to go over the notes from the classroom lecture for matter. Uh, I'm going to try to kind of replicate the discussion we had in class. Um, it might be a little different just because I'm doing it without having people to interact with, but I'll try to get as close as possible. So this will be the first page of this, the matter notes. We'll do a different one to replicate what we do the second time with the rest of it, but matter, anything that has both mass and volume, definition. And then the definition of mass is the amount of matter in an object. They're kind of circular, but it is what it is. All right. So we're going to talk about properties of matter and changes in matter. The difference between properties and matters is a grammatical one. Properties are characteristics, which means they are adjectives, they describe, descriptors. Changes are actions, which means they're verbs. Okay? So starting with properties of matter, we can split both properties and changes into two categories, physical and chemical. So physical properties are properties that can be observed without altering or changing the identity of the substance. In other words, you can observe it and it's still the same thing. So I've given some examples here. Density. Okay, you can observe the density of something. Put styrofoam into water. It floats. You can observe the difference in densities like that without actually changing it into something new. Color, melting and boiling points, shape, magnetism, viscosity. Viscosity is essentially how thick or runny a liquid is. The higher viscosity is thicker. Lower viscosity is thinner or more runny. Conductivity, something's ability to transfer heat or electricity. Luster is shine. Volume, mass. So I've given some specific examples. Color of gold, iron's attraction to magnets, the thickness of honey. So like honey would be a high viscosity liquid, water would be low viscosity. A wire's ability to transfer electricity, stuff like that. Okay. Chemical properties. These are characteristics that cannot be observed without altering the identity of the substance. In other words, in order to observe it, you have to turn it into something new. So examples, flammability, reactivity in general. Okay. Flammability of clothing, specific iron's ability to rust, copper's ability to oxidize or create a patina. So it has to be something that, in order to observe the property, you have to turn it into something new. Now, you might look at a piece of paper or something and say, well, I know that's flammable and I don't have to watch it burn. I know it's flammable. But if you think about it, the only reason you really know it's flammable is one of two things. Somebody told you, or two, you had a previous experience with it burning. So if you think about, to actually observe the flammability of something, you have to try to light it on fire, to try to burn it. Okay, that's the only way. And if you burn it, you turn it into something new. Okay, so that's a chemical property. All right, on to changes, the actions. Again, splitting it into physical and chemical changes. Physical changes are any action or change that does not alter the identity of the substance. The substance remains the same. So generic examples, cutting, crumpling, tearing, smashing, crushing. Now, some of these are ones that people sometimes get wrong. So like dissolving. Dissolving is, and the reason is because we use the term dissolving in several different ways in everyday talk. Like we use it for dissolving sugar in water, salt in water. But we also use it if like you had acid and you dropped it onto something and you say, oh, the acid is dissolving that. They're eating away at it, you know? But in science, those are two actually very different things. The dissolving that happens like when an acid hits something, that's an actual reaction. It's actually reacting with the substance. Okay, whereas dissolving salt or sugar in water, that actually is the water surrounding the molecules and splitting them apart so much that you can't see them, but it's not actually changing those substances. Okay, so true dissolving, the way we refer to it in science, is a physical change. Okay, and then all state of matter changes. So state of matter changes are like melting, freezing, boiling, vaporization, condensation, sublimation, deposition, all those kind of things, evaporation. Those, all that's happening in those is the molecules are getting further apart or closer together. It's not actually changing the substance. So you take water and you freeze it, it's still H2O, it's still water. You take water and you boil it, turn it into a gas, it's still water. Okay, you're not changing it. Those are physical changes, not something new. So specific examples, melting wax, melting specifically, tearing a piece of paper, boiling water, crushing aluminum can, dissolving salt and water like we talked about, minerals forming on a faucet. That's evaporation of water leaving the minerals behind, which is a physical change still. Okay. All right, chemical changes. These are changes that do alter the identity of the substance, turn it into something or more than one thing new. Examples, burning, oxidizing, any kind of reacting in general would be a chemical change. So specific examples, wood burning, a car rusting. A car rusting is iron. That's iron's way of oxidizing, reacting with oxygen in the air. The Statue of Liberty oxidizing, getting a green patina. So we talked about this. I'm going to pull it up here. The Statue of Liberty, if you didn't know, originally the Statue of Liberty looked like this. Over the time throughout the years, it's turned into this. Okay, now it's not dirt, it's not dirty. What happens is the copper that's in the Statue of Liberty reacts with oxygen and water vapor and stuff in the air, and it actually undergoes a chemical change. This is essentially copper's version of rusting. Okay, but it happens a lot more slowly. It happens a lot more slowly over time. Well, some people ask, well, why don't they like clean the Statue of Liberty or whatever? What you have to realize is that just like in rusting, when this reaction occurs, it's actually turning into something new. So that green layer isn't copper anymore. It's actually a new layer. Now, there's still copper underneath it because not all of it changed, right? But if you kept on removing that patina layer, that green layer, it would expose more copper and it would look like the 1886 one again. But again, over time, it would react with oxygen and water vapor and stuff in the air, and it would look like this then again. So slowly, it would kind of eat away at the Statue of Liberty. By leaving it this way, that actually creates a little bit of a protective coating because the air and the oxygen can't get into where the copper metal is because it's got that coating over it. So it actually slows down the process. It doesn't stop it entirely, but it slows the process down considerably. And over time, though, with the reactions and the oxidation, it does weaken the structure and kind of eat away at parts of it. And over its history, there have been times when the Statue of Liberty, when they've had to close it and they've had to do renovations on it and kind of like increase the supports for different areas that have become weak through the oxidation over time and stuff. Okay, so that's an example of a chemical change. Leaves turning color. So the change in color, like color is a physical property, but it's a sign of a chemical reaction occurring inside the leaves that are changing them. Okay. All right. Now these, cooking an egg, baking a cake, those can be difficult. So anything that is grilling or cooking or baking, anything like that is a chemical change. And they can be hard because we call it the same thing before and after. So like you have a steak, you throw it on the grill, you grill it, you take it off, it's still a steak. We don't call it something different. So it's like, well, it's not something new. Yes and no. Okay. Yeah, we still call it a steak, but actually the act of grilling it actually changes the chemical compounds inside the steak. Or think about an egg, because an egg's a really like that's a really easy one to think of. You have an egg before, you have an egg after you cook it, but it looks totally different. That's because it is actually different. The heat has broken down and denatured the proteins inside of it and changed them into something new. And so it really is a chemical change. And that's why it tastes different to us too, is because it's changed chemically the compounds inside. All right. So baking, cooking, grilling, any of those type of things are all chemical changes. Okay. And then the last one, fruit and vegetable ripening. So this is another one. Like people might like, well, it's a banana when it's not ripe, and it's a banana when it's really ripe. It's the same thing. Okay. Yeah, we call it the same thing, but there's a vast difference to it. Think about a banana. If you've ever eaten a banana before it's ripe, like when it's kind of green, it tastes really like bland, um, there's very little taste at all. Somebody in first hour said starchy, which is a really good description. Tastes very starchy. Uh, and if you think about banana, if you eat it when it's very ripe, it's very sweet. The more ripe it gets, the sweeter it gets. Okay. And that's actually because it's undergoing inside the banana is undergoing chemical changes. The carbohydrates that are found in the banana, there's a lot of carbohydrates, and as it ripens, those carbohydrate chains break up and turn into sugar. So the longer it goes on, the more it ripens, the sweeter it tastes because literally there's more sugar in it and there's fewer carbohydrates. When you start out, like the person said, it tastes starchy because it's got a lot of carbohydrates in it. Okay, but over time, those break down into sugars, and that's where you get a sweeter taste. Okay, and similar to that, if we go back to the cooking idea, if you've ever tasted the difference between like a raw onion and an onion that's been sautéed or cooked a lot, a very similar thing happened when it's raw. It's bitter. It's got the carbohydrate flavor, and that kind of sharp taste to it. And you cook an onion for a long time, and you get there's actually a process called caramelizing. The heat breaks down the carbohydrates and turns them into sugars. And caramelized onion, after you cook it and saute it for a long time, it's actually got a much sweeter flavor to it because there's literally more sugars in it than when you started because you've broken carbohydrates down into sugars. So those are examples of chemical changes. All right. Okay, that's where we're going to stop for this lecture. Actually, you know what? Really quickly, I'm going to also walk through, because I did this in class as well, the homework. So for the physical versus chemical property page, all you're going to be doing is going down here, and if it's a physical property, you mark that. If it's a chemical property, you mark that. So like blue color. Okay, that's something you can observe without turning it into something new. So that would be a physical property. Okay, like that. So you just mark one or the other based on what it is. Okay. Then the page 19, the physical versus chemical changes. Again, similar thing. You're going to just put physical or chemical change. Okay, you don't have to write change. You can put physical or chemical, but I want you to write it out. So like sodium hydroxide dissolves in water. We talked about dissolving. The technical scientific term dissolving. That's actually a physical change. So you'd write physical. Okay. Hydrochloric acid reacts with potassium hydroxide to produce. So reacts with tells you chemical change. It's turning into something new. Okay. All right. If you guys have questions on anything, text me or message me, and good luck. I hope it goes well for you.